Welcome to lecture 39 of the course Modeling and TCAD Simulation of Solar Photovoltaic Cell. In this lecture, we will show you how the Poisson equations are linearized using the notations that is discussed in the last lecture. In last lecture, we discussed the meshing techniques, uniform and non-uniform meshing. We have discussed advantage of non-uniform meshing. Also, you are familiarized with the notations used for discretization that will be used in this lecture. So, in this lecture, we will discretize the Poisson's equation using the notations discussed in last class. Say discretization of Poisson's equation. We know the form of Poisson equation, that is del square phi is the potential, is equal to minus q by epsilon into the charge density. So let us write in one dimension. If we write in one dimension, d square phi dx square, say along x direction the variation of potential is there. So that will be is equal to 1 by epsilon 0 epsilon rs. By combining epsilon 0 and epsilon rs, it becomes epsilon 0 q times p minus n plus na plus nd plus minus na minus p plus nd plus minus n minus na minus. Now we have to write in the linearization form using the finite difference method. So how can you do that? So that can be done using the notations. Again, I am mentioning the notations. If you remember, I can redraw whether you remember or not. This is ij. Next point at a distance delta x, that is I plus 1 comma j, that is this is I j plus 1, this is I j minus 1, this is I minus 1 j, half point I minus half j, I plus half comma j, and similarly here I j minus half I j plus half. So you write the equation. So del square phi del x square formula we know. So we can write phi I minus 1 j minus twice phi I j plus phi I plus 1 j divided by delta x square. That is a second order derivative formula I am using. Delta x square plus psi, is phi I j minus 1 minus twice phi I comma j plus phi I j plus 1 divided by delta y square. Because two-dimensional case we are considering, so differentiation along x, along y, that is there in one dimension. It is, the formula is in one dimension, but it is, we are writing this discretized in two dimension. So this will be is equal to minus q by epsilon 0 epsilon rs into, say, first you have to write the p minus n. So p ij minus n ij, and then nd plus, or let us write only nd here. So nd ij and minus na ij. From the finite difference technique, we have put the value del square phi del x square plus del square phi del y square is equal to minus q by this. So it is coming from del square phi del x square plus del square phi del y square, that is equal to minus q by epsilon 0 epsilon s into the carrier concentration minus n plus nd minus na. You observe here, we have used the formula written in equation number 116, if you remember. That is, just you remember in this way, phi I minus 1 j, that means phi, this point, this value, my plus phi I plus 1 j, this value, minus twice phi I j, minus the twice into the center value, divided by delta x square. Delta x is nothing but the gap between these 2 points. Here the half point is not being used, although I mentioned I plus half, that will be used later. So as per notation, let us draw the notation within a box. And similarly in y direction, this value ij plus 1 plus ij minus 1 minus twice phi at the central point, middle point, ij, divided by delta y square. and the order of error in this case, it is in the order of, error is in the order of, or approximation is in the order of delta x square. Error is in the order of delta x square, delta y square. Delta x, actually delta x whole square, delta y whole square. And if we use the other form, that is for non-uniform meshing, here we have used the uniform meshing. This formula for this is for uniform meshing, and you can see the uniform meshing formula, we can write these things. For non-uniform meshing, what the changes? Say for non-uniform meshing, the same formula we have to write here in this way: phi I plus 1 j minus phi I comma j by ai minus phi I j minus phi I minus 1 j by a I minus 1. This whole divided by ai plus a I minus 1 divided by 2. This is the x direction, along x direction derivative, and this along y direction derivative. The same way we have to write phi I j plus 1. Here the change in the j direction, minus phi I j divided by bj minus phi I j minus phi I j minus 1 divided by bj minus 1, just like here also bj plus bj minus 1 divided by 2 is equal to minus qy epsilon 0 epsilon rs into ndij minus nij plus pij I comma j. Comma is missing. If missing this, you just consider, because same comma is there actually. Minus na I comma j. Why it has been replaced by ai and ai minus 1? Because in non-uniform meshing, ai may change. That is, ai for all values of I are not equal. That's why we have defined in terms of ai. If you see the notation, you can remember this ai. ai we have defined ai as x I plus 1 minus xi, and bj is defined as y j plus 1 minus yj. Ai is r not equal for not same for all I. Bj's, these values are not same for all j, because this is non-uniform meshing. So that's why it is represented in terms of AI. What it represents, if you minutely follow, phi I plus 1 j minus phi ij, that is what is incremental in the right side point with respect to the central point, say ij, divided by ai, the distance between these two, because xi plus 1 minus xi plus 1 minus xi, that is ai. So this phi I plus 1 j, there is a potential phi at xi plus 1 point and then xi point. So this divided by ai, that is what is the increment of potential in the right side from the ij, divided by the distance, there is a par length, minus in left side how it increases. In that case, phi ij minus phi I minus 1j, that is phi potential at xi and potential at xi minus 1, that is xi minus xi minus 1. So this will be ai minus 1, because as per notation xi is ai here. So if it is ai minus 1, that is if it is xi and it is the difference is taken as xi I minus xi minus 1, that is x, here we can write in a small space x minus xi minus 1, that will be ai minus 1. So increment in right side of the point ij par length minus increment in the left side of the central point by par length, this difference divided by the total, this ai plus ai minus 1 by 2, that is 2 distance by 2, because this overall increment, this gives you the d square phi dx square, del square phi del x square. Similarly, del square phi del y square, that will be suffix will change in j domain. I remains same, all cases I are same, but j changes, and that's why this is bj minus 1 in the same way. So in non-uniform meshing, we are using the notation aia minus 1, because they are not equal. Now whether uniform meshing or non-uniform meshing, whatever may be the case, these types of equation you have to write for all nodes. This for ij nodes I have written. This particular equation we have written for a ij node, for a particular node, say I comma j, maybe 2 comma 3, maybe 4 comma 4, whatever. So for all the nodes, if you write, there will be a series of such equations. How can we solve those equations? Because so many algebraic equations are coming. In that case, we have to take the help of matrix solver, matrix method. So in the steps for the solution, numerical solution, we have shown a block diagram, and after discretization, there was a block matrix solver. You just correlate with that. So this matrix solver, so this equation can be summarized or can be written in the form of matrix, where so discretized Poisson equation can be written in the form of matrix. So discretized Poisson equation can be written equations written equations for all nodes written in the form of matrix. Say A, this is a matrix, into the phi, that will be is equal to say B. A is the coefficient matrix. A will be the coefficient. A will be the coefficient matrix of the potential. Coefficient matrix. Coefficient matrix, that is coefficient of potential. And B, that will be the matrix containing Q, etc. These terms, containing terms associated with N, P, etc. So in this way, we can reach the matrix equation. And how to solve the matrix? There are several matrix solver methods are there. You can take any of these, say Gauss-Seidel method, SOR method, to solve this matrix to get the potentials. And after getting this potential, you can calculate the electric field also. And the electric field is calculated by some equations related to the potential. So we know the relation of electric field. How can we calculate the electric field? Electric field along x direction, x, I comma j, because at ij node potential is calculated, is shown in last thing. So that will be minus del phi del x. This is the formula. So this can be written as phi I j minus phi I plus 1 j divided by ai plus some error. Error is of the order of ai. So let us cancel this, no issue. This error is for we have written, because this forward formula we are using here. The derivative, we are taking the forward difference method. That's why phi ij minus phi I plus 1j by ai, because minus sign is there. Actual formula is phi I plus 1j minus phi ij, but due to minus sign, it changes. That is its position, phi ij minus phi I plus j. Similarly, ey ij, that will be minus del phi del y, and that will be nothing but, again you can say phi ij minus phi I j plus 1. Again the same thing, actually phi I j plus 1 minus phi I j by bj plus some error of the order of bj, but it is error is small, neglected. And after getting this ex and ey, e, that can be obtained as Ex square plus Ey square. Eij, that will be Exij plus Uij square. In this way, electric field can be obtained. And if we use the central difference formula instead of forward difference formula for electric field, more accurate result can be obtained. Of course, the central difference technique gives you the better, that is less error. So in that case, using central difference, you can say Exij, that can be written, just you have to take I plus 1 and I minus 1, and also j plus 1, j minus 1 point, and you have to divide this into 2 delta x, that is phi I minus 1 j minus phi I plus 1 comma j by twice ai. Delta x is nothing but ai plus of the order of delta x square or ai square. But this this is error, or Eyij also, that will be phi I j minus 1 minus phi I j plus 1 by twice bj plus some error, that is of the order of bj square. This is error. This is cancelled. So in this way, either using forward difference technique, this is the forward, using central, this is forward difference, technique, we can calculate. So in this way, you can discretize and you can solve. Let us take an example of discretization of Poisson equation. Let us consider a region, suppose a square shaped region we are considering, and we have suppose few grids. For ease of example, I am considering the small number of grids. This point say 0 0, this is 1 0, this is 2 0, this is 3 0, this is 4 0, this is 0 1, 0 2, 0 3, 0 4. These points are these two surfaces. There is the boundary of the region and this boundary, and this point will be 4 4, and other points also, other nodes, mesh nodes, say accordingly we can write. Now if the boundary condition is given that say potential at these two boundaries, that is 0 0 to 40 and 0 0 to 04, potentials are 0. So this is the boundary condition. Potential at two boundaries is 0. So we can write phi at 0 0, that is equal to phi at 1 0, that is phi at 2 0, say phi at 3 0 is equal to phi at 4 0, all are 0, and similarly phi 0 1 is equal to phi 0 2 is equal to phi 0 3 is equal to phi 0 4 is equal to 0. For simplicity, we may write, instead of phi 0 0, let us consider as a simple phi with suffix 0 0, no comma, no bracket. So this for our simplicity of writing the equations. So this point, suppose this is 1 1, so if we like to write the Poisson equation at this point, say this is Ij, say Ij, this is equal to 1 1. This point, Ij point is 1 1. So what will be the phi Ij? We can write the Poisson equation in two dimension, we know, that is del square phi del x square plus del square phi del y square is equal to minus q by epsilon 0 epsilon rs into p minus n plus nd minus na. So phi 1 1, if we consider as a by Ij, so this and the distance between these two nodes, that is step size, say this is h, and also this is delta y, this is suppose also h, this is delta x. Now from the finite difference formula of the derivative, we can write phi 0 1, only simply 0 1, this point, phi 0 1 plus phi, this point, this will be 2 1 minus twice phi 1 1 divided by h square. So this is the finite difference formula. Phi ij is equal to phi, this del square phi ij del x square, that is del square phi ij del x square. This is nothing but phi at 0 1, that is the previous point, I minus 1 j, I minus 1 j means this is 0 1, plus phi I plus 1 j, I plus 1 j means here I plus 1 means 2 1, this is j, minus twice the value ij, that is phi 1 1, divided by h square. So this is del square phi del x square for this node phi 1 1, plus this side again we can write phi at this point, that is phi 1 1 2 plus phi 1 0 minus twice phi 1 1 divided by h square. That will be equal to minus q by epsilon 0 epsilon rs into p at ij. P at ij means p at 1 1 minus n at 1 1 plus nd at 1 1 minus na 1 1. Similarly, for other nodes, for this node I have written, similarly for other nodes, say phi 2 1, this node is 2 1 node, that can be written here phi 2 1 del square phi del x square. So phi 1 1 plus phi 3 1 phi for node 1 comma 1. This is for node say 2 comma 1. So phi 1 1 plus phi 3 1 minus twice phi 2 1 divided by h square plus this point will be 2 2, this is 2 0, so phi 2 2 plus phi 2 0 minus twice phi 2 1 by h square is equal to minus q by epsilon 0 epsilon rs p at 2 1. This is the node for 2 1 minus n 2 1 plus nd 2 1 minus na 2 1. In this way, we can have a set of algebraic equations. But you find that the boundary conditions, that is phi 0 0, phi 1 0, phi 2 0, 3 0, etc. at 0. If you put these values, so this 0 1 will be 0. So this will be also 0 due to boundary condition. Let us write in a different color pen. This will be 0, that is a boundary condition. Phi 1 1, phi 2 1 is nothing, but phi 1 2 is again phi 1 0. Phi 1 0, this is also 0. And in this equation, there is no 0 is present. So after putting the boundary condition, you can have some simplified version of the first equation. And here you can observe that phi 1 1 is present in this equation also and in this equation also. And other term phi 2 1, phi 1 2 also they are present in both the equations. So some terms are present both the equation, but some terms are not present. However, if we simplify it by removing the denominator part, that is in the right hand side, if you multiply both side by h square, so it will give a simple algebraic equation, and with some coefficients of phi 11, phi 12, phi 21, etc. So all the equations after framing for this grid, you have a set of equations, and that equations you can represent in the form of matrix. And after forming in the matrix, you can simplify by augmentation matrix and diagonalization technique. So some row operations, if you do, you can have a simplified version, and from that you can get the solution. But boundary conditions are required. So there are different techniques to solve these equations that will be discussed in a class by taking an example, specific example with some values of all these hole concentration, electron concentration at the nodes and at the boundaries. But here actually I have shown how can you discretize the Poisson equation, two dimension in case of two dimension. And instead of putting ij, if you put this suffix only, no comma, no bracket, it will be much more easier to express. We will follow these notations for further calculation and simplification whenever we go through the examples. So in this lecture, we have discussed how the Poisson equation is discretized and how the algebraic equation in matrix form is obtained from the double derivative in the Poisson equation, and then solution of these will be taken by a suitable example in some few next classes, in some classes later. This is the reference related to the semiconductor device modeling, but in general there are engineering mathematics books you can follow for numerical techniques. Thank you.